Today what we're going to do is make a start on the section on cosmology, all right? And cosmology is in one sense very, very simple. Cosmology deals with the behaviour of universes, all right? So it's the ultimate in big science. It thinks about the entire universe as a whole, okay? Here's the universe, it's a big round thing apparently, and it's got lots of stuff in it, okay? Now the thing to remember in this section, when I put a dot on the board, it doesn't mean a star, it doesn't mean a planet. Each dot is probably going to be an entire galaxy, all right? Hundreds of thousands of light years across, containing billions of stars. That's what each of those dots is, all right? So we know that our universe is made up of loads and loads of galaxies, and in between them, an awful lot of empty space, okay? There's very large distances, as you know, between galaxies and so on, okay? And cosmology is the science of the universe as a whole, okay? If you've been thinking of astronomy as starting off with the Earth, zooming out to the moon, the planets, the stars, the galaxy, this kind of zooming backwards idea of astronomy, then cosmology is the final stage, all right? It's as zoomed back as you can possibly get, okay? Now, let's think a little bit about what we know about our universe, and I like to think of it sometimes, like most things in science, you can think of them like a little seesaw, okay? There's clearly a couple of forces that are going to be affecting our universe, okay? On the very grand scale that we're thinking of, on this very, very big scale, one force which we've known about since the time of Isaac Newton, of course, is the force of gravity, okay? We know that gravity pulls everything towards everything else, all right? So gravity pulls inwards, it pulls this board marker towards the ground, apples down towards the Earth, keeps the moon in orbit around the Earth, etc., etc., etc. Gravity is all about attracting. It's all about pulling things towards each other, okay? And it works as much on the large scale of a galaxy at, 100,000 light years across as it does on me, dropping a pen or something, okay? Now, that's fine. If gravity were the only force to affect our universe, so you get the universe, bunch of galaxies, gravity, start the clock. The universe is clearly quite old. What would the universe end up like if gravity was the only force affecting it? So run that model for a few squillion years. It would, wouldn't it? Can you imagine what the universe would be like? If gravity was the only thing happening, then gradually everything would just be pulled together, wouldn't it? And you'd expect the universe to be like a big lump of stars and galaxies all clumped in on top of each other, okay? And that's clearly wrong. If you look out at the night sky, that's just not how it is. Just to get the perspective, here's the Milky Way galaxy. We think it's about a spiral, It's about 100,000 light years across, okay? We are a star in one of the spiral arms, okay? And when you look out at the night sky, what are you looking at? You're looking at mostly, not entirely, you're mostly looking at other stars in our spiral arm, okay? So on the grand cosmic scale of things, when you look out at the night sky with your naked eye, you're mostly looking at stars which are also in the Milky Way and are relatively close to us in our spiral arm. You're probably not looking at stars on the other side of the galaxy, and you're probably not looking at stars and galaxies outside the Milky Way, although you can see some, okay? And even on that scale, if you look out, yes, there's lots of stars, but between them, there's this enormous emptiness, isn't there? Okay? So this is clearly incomplete. Okay? We have gravity, as a mathematical formula really, since the 17th century, since the time of Isaac Newton. But it's clearly not a complete model, and cosmology has had a difficult time. You might say the ancient Egyptians had a theory of cosmology, that the sun and the moon were rowed across the sky in boats, etc., etc. But if, no disrespect to them, but if we say a sort of a scientific theory, a predictive theory of cosmology, how long's that been around? Well, it definitely starts with gravity. Gravity is an important force in the universe, okay? But there must be something else, otherwise the universe would just be a big lump, okay? Now, for quite a long time, people bothered about this and went round in circles to a large extent. What is the other force that people just didn't really know? If you want to read into this, there's a nice piece of science called Olbers paradox, which I think predicts that the night sky is infinitely bright or something like that. If this is our model of the universe, then it doesn't work, all right? Universe, lots of galaxies, gravity working away, you get all kinds of nonsense predicted. Common sense tells you it should just be a lump in the middle, and if you read about Olbers paradox, you'll find it's even worse than that, okay? And that's why cosmology's had a difficult time since the time of Newton. I think somebody once said you can tell how important someone's discovery is by what gets named after them, all right? And the next big discovery really doesn't come until the start of the 20th century. With a gentleman, again, if we went into Skipton High Street and asked people, do they know what this particular scientist did, I think they would probably know the name of a gentleman called Edwin Hubble, okay? But probably fewer of them would know exactly what his contribution was, but his contribution was enormous because he basically made the science of cosmology work, all right? If you've only got gravity, I like to think of it, you've only got one half of the seesaw, and for nearly 300 years, cosmology was a difficult area because it kept predicting things that just aren't true, okay? Edwin Hubble, who's now got his name on, what's named after Edwin Hubble? Space Telescope. Think about it, the first telescope to be placed in orbit around the Earth. Do you follow? Was it named after Isaac Newton, Johannes Kepler? No, Edwin Hubble. And you might think, well, what's so important about that, about him? It's his discovery. His discovery at the start of the 20th century basically started the science of cosmology to work properly, because Hubble basically filled in what's on the other side of the seesaw, which for many hundreds of years people had not really understood. Okay, so we're going to have a look at Edwin Hubble's discovery at the start of the 20th century. Okay, but we need to do it quite carefully. We need to think about what it is that he actually discovered and to be clear what he was actually doing. Okay, quite easily misunderstood Hubble's discovery. You see textbooks where it's clearly not been quite properly understood. So let's think a little bit carefully about what Edwin Hubble discovered. This enormously important discovery at the start of the 20th century. Okay? Now, if you do Google image for Edwin Hubble, you can often find pictures of him in his tweed jacket with his pipe, standing next to a whacking great telescope in America. And yes, that's what he was doing. Edwin Hubble lived on the Earth, as you do. He had a huge great telescope in America. Okay? And often that's what makes astronomers great. They were just the next person to have the next biggest telescope, and so they made the next biggest discovery. Anyway, Edwin Hubble was looking out from the Earth with a large telescope. Okay? Now, two things you need to understand about Edwin Hubble's discovery which are not well explained in any textbook. Okay? First of all, what he was looking at. He wasn't looking at the planets. All right? This is the early 20th century. That's all been done. He wasn't looking at, here's Edwin Hubble, here's some nearby stars. This is going to get difficult to draw in a minute. There's the Milky Way galaxy. All right, so can you imagine? That's our spiral galaxy, the Milky Way. Okay, it's a bit out of scale, but we're in one of the sort of spiral arms. You with me? Was he looking at stars in our region of the galaxy? No, not really. Was he looking at stars elsewhere in the Milky Way galaxy? No, not really. Was he even looking at, there's a very famous galaxy, another galaxy of stars near ours, called Andromeda. Was he looking at the Andromeda galaxy? Oh, no, not really. That had kind of been done. People had realised the Andromeda smudge of light is actually not a cloud of gas near us in the solar in the Milky Way. It's actually another galaxy. Okay? Edwin Hubble, he didn't realise it at the time, but he was the first person to be looking beyond galaxies like Andromeda. Now, what do we mean by galaxies like Andromeda? We mean galaxies that are linked to ours by the force of gravity. The Milky Way and Andromeda are actually going round each other very, very slowly. You with me? But in years to come, you will actually be able to see the Andromeda galaxy much better because we'll be crashing into it. And there'll be a massive line of stars across the sky. It's a bit like two swarms of bees having an accident. Can you imagine that? But we are gently, I think they're bigger than us, and we're falling towards them. Whatever, we're coming closer together. Okay? And there are other galaxies around. Okay, there's other galaxies that are around which are close by, which are linked to ours by the force of gravity. Okay, there are two very famous ones, which you can't really see from Skipton. The Large Magellanic Cloud and the Small Magellanic Cloud are two little galaxies linked to the Milky Way by gravity. They're only really visible from the southern half of the Earth, hence they're named after the explorer Magellan, who was one of the first to see them from places like Europe. There's a famous galaxy in the constellation of Triangulum, which is a very boring constellation of 3 stars. And all these galaxies are linked to our own, okay? How many of these can you see with the naked eye? You can see the Large and Small Magellanic Clouds with the naked eye, but you need to be in Australia. The Andromeda Galaxy, you can see, if you Google up for it, it's possible to see the Andromeda Galaxy. It's easier in the summer, I think. But it's not very bright. It is quite hard to see, but it's amazing there because you are looking at an object which is not part of the Milky Way galaxy. So although it's a bit of a chore, it's worth trying to find the Andromeda Galaxy because then you can say, I'm actually looking outside of our own Milky Way galaxy. Now, this group of galaxies, if you can mentally put a big loop around that, this group of galaxies has a very important but rather boring sounding name. It's called the local group. Okay? These galaxies, and you do need to know roughly their names, the Milky Way, Andromeda, the 2 Magellanic Clouds, the Large and the Small, and the Triangulum Galaxy, they're examples of galaxies in the local group. Now, local group just means like nearby things in common English, but actually in astronomy, local group means, put some little G arrows next to it, it means galaxies linked to our own by gravity. Okay? Now, Edwin Hubble, I don't think realised it at the time, but he was one of the first astronomers to be looking at galaxies outside the local group. Galaxies which are not linked to the Milky Way by the force of gravity. Okay? Now that's really important for cosmology, that's highly significant. But pretty much most of the astronomy that took place before Hubble had been concerned with looking at stars in the Milky Way, looking at nearby galaxies like Andromeda and Triangulum and so on, galaxies within the local group. And Hubble was one of the first to really study galaxies outside the local group. Why? Because he had a big enough telescope. That's often the way in astronomy. And that's the first thing to get your head around. Edwin Hubble wasn't looking at stars, all right? He was looking at galaxies beyond the local group, okay? And that's why he made the discoveries that he did, all right? If he looked at, you'll see in a moment, if he looked at galaxies in the local group, he wouldn't have made this discovery, and that's perhaps why he has his name on this particular discovery, okay? So, excuse me, that's the first thing, is what Edwin Hubble was looking at. This idea of astronomers looking at stars and stuff like that. Firstly, he wasn't looking at stars, all right? When Edwin Hubble took a photograph through his telescope, every dot would have been a galaxy. Okay, he was looking way beyond that, all right? We're at the start of the 20th century, mirrors in telescopes are very large now, and you can image things which are a very long way away, okay? Is everybody happy with that? And you need to know the definition of the local group, all right? It doesn't mean nearby galaxies. It does, but that's not the definition. The definition is galaxies linked to the Milky Way by the force of gravity. Okay? Now, second thing is what Hubble was actually doing. All right? He wasn't actually looking at the stars, sitting there peering through the eyepiece. Firstly, because the things he was looking at, these distant galaxies, would have been so faint. If you looked through the telescope, you wouldn't have seen anything. What you'd have had to do is to put a piece of photographic film where the eyepiece would have gone and let the telescope track that object for about an hour and then get your piece of photographic film in the old days of photography, put it through chemicals and things, get it developed, and then you would have got a photograph with some dots on. Each dot is a galaxy. Remember, we're looking way outside the Milky Way here. And that's the way Hubble would have worked, all right? And his discovery doesn't come from taking photographs. So if you can imagine, here's the light from this distant galaxy, goes into the telescope, and what he was doing he didn't actually use a prism, but it's the same sort of idea. He was sending light through a prism. Okay, a device in astronomy which we call a spectrometer. Okay, he didn't actually use a prism, he used another way of doing it, but you don't need to know that. In principle, he was putting the light through a prism, which, as you know, will split it up into its different colours. All right, I can't really draw this, but you'll remember red, orange, yellow, green, blue, indigo, violet. If you try this at home, get a beam of sunlight if you can, prism, piece of white paper, then what you get is not a beam of white light, you get all the different colours. The prism changes the light's direction by different amounts for different colours, and that's why they all get separated out into what we call a spectrum. Okay, I can't really draw that, but you've all seen a rainbow with me, you all know. I really can't draw that. All right, so if you can imagine these sort of bands of different colours, like a rainbow. Okay. Now, what's the point of doing that? It looks pretty, but why would you do that? Well, people discovered sometime earlier, and again, they didn't use a magnifying glass, but if you can imagine this, not looking through the telescope, sending light through a prism to break it up into its colours, and then having a look at that spectrum through a magnifying glass. In reality, we would have used a microscope, but it's the same sort of thing. So if you can imagine the spectrum, sort of magnified now, red, orange, yellow, green, blue, indigo and violet, okay? People have discovered, by looking at the spectrum of the sun sometime earlier, they found basically missing colours. If you look very closely at the sun spectrum, to you it looks like a rainbow. If I say which colours aren't there, you say, well, they're all there, red, orange, yellow, blah, blah, blah. But if you look very closely, there are, for example, particular shades of orange, a particular shade of yellow there, a particular shade of green, which are not present, which are missing, and therefore appear as dark lines, okay? And these are called spectral lines, and that's the key idea, that's the second big idea, is that Edwin Hubble was looking at spectral lines. He wasn't looking at the stars, he wasn't, beg your pardon, looking at the galaxies. He was taking the light from the galaxies, splitting it up using a spectrometer, and looking very closely at the spectrum for the missing colours. That's a good phrase for your margin. The missing colours or spectral lines in the spectrum. Now, why would you do that? Well, the reason for that is, I can draw the right arrow, a really good description, and one that I recommend you jot down, is what's the point of studying spectral lines? Well, it's basically a chemical fingerprint. If you know the exact pattern of spectral lines, you can say, I know exactly which chemical element made that light. I know what temperature it was at, I know what other elements were present, I know what magnetic field it was in. It's almost, as we said here, a chemical fingerprint for the thing that produced the light. Now, this is really important because think how far away that galaxy is. We haven't visited it. We're not going to be visiting it anytime soon. And so, it's a really important idea, is this ability to find out about the light from distant stars and distant galaxies, okay? If you think about even the closest star at 4.5 light years, we're still not going to be visiting that anytime soon. And so, analysing the light, breaking it up into its spectrum, looking at the lines and using them, I hope you've got this bit written down, as a chemical fingerprint. Okay? That's the second thing you need to understand about Hubble's discovery. He wasn't looking at anything nearby, he was looking at things outside the local group, things not linked to us gravitationally. And secondly, he wasn't looking through the telescope, he was looking at the pattern of, and these are words you need for the exam, spectral lines. All right? Why? Because they are essentially a chemical fingerprint. When we talk about the star having a particular temperature, or a galaxy or a star having a particular temperature, particular elements present, etc., how do we know that? Because we've never been there, we've never sent a probe to a nearby star. The answer is we get it from the pattern of spectral lines. Okay? And in Edwin Hubble's line of work, you would get to recognise these. So when one of these came up, you think, oh, that's helium, oh, that's hydrogen, or something like that. You would recognise the pattern, literally like a chemical fingerprint. Okay? Right, we are going to stop there. I know it doesn't seem very much, but Hubble's discovery is very easy to misunderstand, all right? It's really important you've got these two ideas of the local group and the spectral lines, all right? If you've got those two things straight, Hubble's discovery next time will make perfect sense, okay?